So definition, angular velocity. Well, wait, let's back up. What's linear velocity? What's the definition of linear velocity? So linear velocity, the way to remember that is you could remember that formula, distance equals rate times time. You could change the R to V for velocity. V usually stands for linear velocity. Change the R to V and solve for V. So if you change the R to V, you get distance equals velocity times time, right? Distance traveled equals velocity or rate times time. What's velocity going to be? If you solve for V, d over t, right? If you ever get confused with stuff like this, grab a hold of an everyday example in your life. Your speedometer, right? Miles per means divide, miles per hour, right? Oh, that's d, that's a particular value, particular unit value for d and t. Miles per hour, yeah. Oh, that's the definition. Take your distance traveled, oftentimes that's called s, and divide by t, and you get your linear velocity or average linear velocity in a lot of cases. Okay, so what would be a definition that would make sense for angular velocity? Picture a wheel turning about its axle. So angle measure over, so how fast is it spinning per unit of time, right? Or just over time. Yeah, so whenever we talk about a velocity, we're going to create a fraction, and the denominator is going to be a rate of change, for instance. It doesn't have to be a velocity. Any sort of rate of change, like calories per hour, if you've ever been on a treadmill, right? You might have seen that. That's a rate of change. But it's going to be whatever you're measuring that's changing over time, okay? So for angular velocity, theta is going to be, let's not call it theta, let's call it omega. Okay, looks like a W, but it's a little Greek symbol, omega. Why that means angular velocity, I don't know. That's just how the physicists said to do it. Omega stands for angular velocity, and it's going to be your angle measure in radians, theta, over time. So theta over t. So I just wanted you to see the relationship. They're both rates of change. But angular velocity, it's the angular rate of change. How is the angle being, how much of the angle is being swept out over time, right? But does everybody see the connection then? Oh yeah, anytime you have a rate of change, it's going to be some measurement over time, over t. So a wheel is rotating at 200 RPM. What does that stand for? Revolutions per minute. It's going around and around 200 times per minute, right? It's going around 200 times per minute. Find the angular velocity in radians per second. Okay. So let's write down what we have. We have 200 RPM. I'm going to write it as REV for revolutions. And then the division bar is the P. It's per, right? So it's 200 revolutions per 1 minute. I'm going to write it like that. 200 RPM, 200 revolutions, REV, division bar over 1 minute. That's what that 200 RPM means. It's equal to that. It's equivalent to that statement. Now, angular velocity, we're going to have to multiply by the appropriate conversion factors. So let me write down what we want and hopefully leave enough room. So eventually, through multiplying by the appropriate conversion factors, we want the units of our answer to be in radians per second. And this is one of the rare instances where I will write out the word radian. You could put radian or radians, I don't care, per second. Guys, you didn't have to know that above definition to know, to realize what to do here, what you're after. Oh, you want your answer in radian or radians per second. Oh, well, that is, though, the definition above of angular velocity. angle measure per unit of time, right? So we're finding angular velocity here. But in order to do this problem, you don't really have to think in terms of the above definition. You just have to think in terms of the units. Oh, it tells us we want the answer in radians per second. Oh, it tells us what we're after. All right, well, let's think about what we know. I think converting from minutes to seconds is not going to be a big deal. Yeah. So we'll do that last. Revolutions. Oh, okay. So I want to convert revolutions to somehow radians. So I guess my question to you is, one revolution would be how many radians? 2 pi. There's our conversion factor, but we have to set it up right. We have to get the right thing in the numerator. So we want radian measure in the numerator, right? So here's my first conversion factor. Okay, I'm going to write down the units first, and then the numbers will follow. So what do I want to go away? Think of it that way. I want REV to go away, right? So that's going to have to be in the denominator so that they cancel. And then what do I want to stick around? I want radians to stick around. So how many radians per revolution? 2 pi. There's 2 pi radians per 1 revolution, right? And so we just created our own conversion factor. 2 pi radians is equal to 1 revolution. How do you make a conversion factor? Divide one side by the other. 2 pi radians per 1 revolution. So you know that revolutions will cancel. We'll be left with radians. So you know this numerator will be correct. But now we need to get seconds in the denominator and not minutes. So what's the conversion? So, okay, we want minutes to cancel, so think about it like this. Minutes has to be on top because minutes over here is on the bottom, right? So it's got to be minutes to seconds. And there's no thought involved except what cancels with what, right? So minutes, not that you can't think about it. You could do it by thinking about it as well. Minutes to seconds, we want to convert minutes to seconds. Oh, minutes in the denominator. To start with, put minutes in the numerator for your conversion factor. Okay, and then what's the relationship? This one you know by heart. 1 minute to 60 seconds. So let's check our work here by actually canceling the units. And if we do that, we'll have the revolutions cancel. We want to end up with radians per second. We'll have the revolutions cancel. We'll have the minutes cancel. And you can see that the radians and the seconds will be left. So you're pretty darn sure you did it right. Okay? All right. And that technique, like I say, works great in you got a lot of units in chemistry and physics. That technique works great for analyzing units. It's actually called unit analysis. Well, let's write out what it would be if you multiply it. So yeah, you'd get 200 times 2 pi. So you would have 400 pi over 1 times 1 times 1, 60. Radians per second. I don't know exactly what that looks like as a decimal. In a lot of these problems, you're going to need to convert it because it's nice to have an idea of what it looks like. So would you take out your calculator, go 400 times pi, hit the pi button, divide by 60. Let's have more than one person doing it because it's surprisingly easy to hit the wrong button. 400 pi. You could simplify it first. What if you wanted an exact answer? What if this were a test question and I said, just give me an exact answer? So, yeah, you could just simplify the fraction 400 over 60. Don't forget the pi on the end, right? So 20 goes into 60 how many times on the bottom? 3. 20 goes into 400 how many times? 20 times. Yeah. And then don't forget the pi. But if you're asked for an approximation, is that step necessarily? No, just go right to the calculator. What do you get when you take either 20 pi divided by 3 or 4? It's actually easier to punch that in the calculator, though. Or 400 pi divided by 3. 20.94? Okay. So approximately 20.94 radians per second.